Hello everyone. So in this lecture, we will briefly review the matrix multiplication, and we will also recover the contents that we have reviewed in the last lecture, the one-dimensional groundwater modeling. So let's think about two equations like a1x plus b1y plus c1g is equal to d1. And the second equation is a2x plus b2y plus c2g is equal to d2. And these two equations can be lumped into a single matrix equation like a1 b1 c1 a2 b2 c2 times x y g is equal to d1 d2. Here there are two column vectors. Let's denote this vector as x, and this column vector as b, and this matrix as t. Then for matrix multiplication to occur, the dimension of there are some rule regarding the dimension of these matrix and columns. So for example, this T matrix is in the dimension of 2 times 3. Here the first argument is the number of rows, and the second argument is the number of columns in the matrix. And this is 3 times 1, and this is 2 times 1. And the rule that I mentioned is that the number adjacent to each other should be always the same. For example, here the number of columns of this matrix is 3, and the number of rows of this column vector is also 3. And because they are the same, this matrix multiplication can be done, and the result of the multiplication is always from this first and the end of these matrices. For example, here the number of rows in the first matrix is 2, and it is appearing here as 2 as well. And the number of columns of this column matrix or column vector is 1, so we have here 1. And the rule of the multiplication is that if you think like this as this A as a single column vector and the other columns as well, then you can think that these are the coefficients for each matrix. So for example, the first column will be multiplied by x, and this second column will be multiplied by y, and third by z. So that means it will look like a1 a2 times x plus b1 b2 times y plus c1 c2 times z, and this is of course will result in these equations, and the right hand side would be d1 d2. And please remember this basic rule of the matrix multiplication, because this is the format of the system equations that will be solved for groundwater flow modeling. So then, keeping this in mind, I will review what we covered in the last lecture, the one-dimensional groundwater system modeling. Okay, then let's review the the one-dimensional ground water flow modeling that we covered in the last lecture. So we started from the one-dimensional Reynolds equation that is written as divergence of Darcy flux is equal to 0. This is Reynolds equation, and in one-dimensional space, this can be written as dx times dx over d of minus k del h, which is the Darcy flux, is equal to 0. And we take integral of this equation, and for arbitrary cell I, where the cell is the segment of the discretized system of the groundwater domain, system domain, I minus 1, I plus 1. And for cell I, we should take integral from, we have denoted the cell interfaces as I minus half and I plus half. And for the brevity of the notation, from now on, let's denote the cell interfaces as L and R, where the L stands for left and R stands for right with respect to cell I. Then the integral should be happen at so let's denote the cell interfaces as L and R, left and right with respect to cell I. Then the integral should happen between L and R. And this gives us Q L plus Q R is equal to 0. Here 0 is coming from the rule of mass conservation. And we learned how to derive the transmissibility term and how to express this Darcy flux using that transmissibility term. So here this can be written as minus TL H I minus 1 minus H I plus TR times H I minus H I plus 1. So, and this is equal to 0. And this can be written as, for cell I, minus TL H I plus TL plus TR H, here HI minus 1, HI plus TR, no, this should be minus TL times HI plus 1 is equal to 0. And this is the general expression for cell I. And we also derived this kind of equation for the boundary cells, where different boundary conditions are considered. So let's begin with the first boundary cell, where we considered the flux boundary. So for cell 1, the boundary condition was the flux boundary, where the flux is given by Q bar. And here the left and right cell interfaces is here, L and R. Then we can write again the mass balance equation, where minus QL plus QR is equal to 0. Then because the boundary condition is flux boundary, where the influx is Q bar, this QL should be replaced by Q bar. So we can fully rewrite this equation as minus Q bar plus QR is in the form of TR times h1 minus h2 is equal to 0. So this equation, so for cell 1, we can write down this equation again, like TR H1 minus TR H2 is equal to Q bar. This is the equation of the cell 1. And let's think about the last cell where we considered the head boundary. So there were n cells. So the index of the last cell should be n. And it looks like where we have head boundary as much as h bar, and the cell indices like n, m minus 1. And here the cell interfaces that we are looking at is here, L, R. Then the integrated Reynolds equation tells that minus Q L plus Q L is equal to 0. Here, if we write down this again, then minus TL HM minus 1 minus HN plus TL HN minus, and this term should be this boundary condition, h bar. And this is equal to 0. So we can rewrite this equation for cell n like if we fully rewrite this again, then we have minus TL times h n minus 1 plus TL plus TL times hn, and this term is constant, so it will be moved to the right hand side. Then we have TL h bar, and this is the result of this discretization of the system. Then because we now fully know how to establish the matrix equations, we can convert this set of equations into matrix multiplication form. So that should be written as, so we will have first the large transmissibility matrix, which is in the dimension of m by m because we have n grid cells. And the unknown column vector is head boundary, head column vector, which we will denote as h, and the dimension of h column vector is n times 1. And we have the right hand side column vector, which we will denote as b, which also has also is in the dimension of m by 1. And this transmissibility matrix T is a tri-diagonal matrix, which means there are 3 lines of non-zero vector in this diagonal direction, and the other elements of the matrix is all 0. And let's say the first row is 1, and the last row of this matrix is n. Then we have arbitrary cell index I, and the the precedent row would be I minus 1, the next row would be I plus 1. And for this arbitrary set I expression, we have the diagonal term as TL plus TL. So this DL. So let's use different color. So for cell I, the diagonal term would be TL plus TR, and the one left word diagonal term would be minus TL. Then we have here minus TR, right? And the head vector would be HI minus 1, here HI plus 1. Like this relationship will continue all the way to this row, the first row, and down to this last row. But there is a caveat, like we have to consider the boundary condition. So the first and the last row would be different from this relationship. So let's start with the first row. We have TL. So here TL, and the right word off diagonal element is minus TR. And here we have H1, H2. And the right-hand side is Q bar. And by the way, this arbitrary cell I has the right-hand side element of 0, right? And let's move on to the last cell. Here we have this diagonal term, TL plus TL. And here we have one off diagonal to the left word, which is minus TL, right? And we have HN minus 1. And the right-hand side element would be TL, H bar. And the other terms are all 0, right? And if we can establish this matrix equation, then we can use some numerical computing software like MATLAB. So let's say we have this this matrix equation as T times H is equal to B. Then using the inversion function of the matrix, we can compute the column vector of the head distribution as T to the minus 1 times B, right? So for your information, in MATLAB code, the grammar for this matrix inversion can be done by T backslash B. Then if you compute this expression in the MATLAB, then you will have the head distribution in this one-dimensional system. Thank you.